And so for nodal analysis, we have a step-by-step process to go through, and one is to analyze the circuit to determine the number of nodes. And so the reality of it is that, we don't really want to call this a node and this a node and this a node, because these points are all connected together. So they are points of equal potential. And so the reality of it is, I suppose, is that we want to call that junction. And so all it is here is at the same potential. And so that's a node. All it is here is at the same potential. And so that's a node. And we got this R3 in between them. Across the bottom of our circuit then, all it is here is at the same potential. And so this is our node. And so really we have 3 nodes in that circuit. Now, it makes sense then for us to select this node here, this large one at the bottom, and call that our reference node. So the reality of it is what we're saying is that at the reference node, V is equal to 0. Now, I'll call this node here A, and this node here B. And so then the voltage at node A, VA, the voltage at node B, VB. And so really there's 2 unknown voltages in that circuit, and they are VA and VB. And of course VB is the answer that we're looking for. So we don't even need a value for VA to answer the question, right? The voltage across the 4 amp current source now is VB. Okay, so we can do nodal analysis, and we have the road equations for VA and VB in order to come up with a solution. And so 2 equations we need. So we start off with node A. And so now there's 4 currents for node A. And we said we would have all the currents leave. So we got one here that we'll call I1, one here that we'll call I2, and one here that we'll call I3. Okay, so the 4th current is from the 10 amp current source, and we may as well have that one coming in at 10 amps. Now we can have them leaving at 10 amps, but then negative 10 amps, right? Because if we change the direction, we got to put a negative sign in there. And so it's just as well to have that one in here and then the other is leaving. So now, for node A then, if we're going to write Kirchhoff's current law, the sum of the currents that enter is equal to the sum of the currents that leave. And so that means that I1 plus I2 plus I3 is equal to 10. Now, we want to write I1, I2, and I3 in terms of Ohm's law. And so in terms of Ohm's law, remember, I is equal to V divided by R. And voltage for each resistor is a voltage drop across it. And current flows from a point of higher potential to a point of lower potential. So the VA subtract whatever's on the other side of it for each one. And so for I1, there's 0 on the other side of it. So VA subtract 0 is VA divided by R1, which is 10. Plus, likewise, for I2, got 0 on the other end of R2 here. So VA subtract 0 over 20. VA divided by 20. Now for I3, we have VA, VB is on the other side. So VA subtract VB is the voltage drop across R3. And of course divide that by R, which is 10. And then that sum is equal to 10. Okay, now we can write these with decimals. And what I find is that generally it's easier to multiply the whole thing by something that'll get rid of all the denominators. And so we want to multiply the whole thing by 20. And if we do that, we have 20 over 10 times VA. So that's 2 VA. Plus 20 over 20 times VA is 1 VA. Plus 20 over 10 times VA is 2 VA. 20 over 10 times negative VB is negative 2 VB. And that is equal to 20 times 10, or 200. Okay, so now we have 5 VA. Subtract 2 VB is equal to 200. And that is equation 1. Okay, so let's do something very similar for node B. For node B, then we also have 4 currents. We have R3, and now R3 leaves is in the opposite direction from the other R3. That's not a problem. We have R4. We have R5. And again, you know, it's just well for us to say that that 4 amp current source enters. And so then, for node B, we can say that R3 plus R4 plus I5, sum of the currents that leave equal to the sum of the currents that enter equals 4 amps. Now, we do follow exactly the same procedure. And so for R3, now if current flows from a higher potential to a lower potential, the voltage drop across R3 is VB subtract VA. So we have VB subtract VA, that's an A, divided by 10. We have now, for I4, VB subtract 0, so VB over 20, plus for I5, VB subtract 0, so VB over 10, and that is equal to 4. So again, we want to multiply the whole thing by 20. And so very often it's the largest number in the denominator. But really I think it should be the lowest common multiplier, right? So 20 divided by 10 times VB is 2 VB. And 20 divided by 10 times negative VA is subtract 2 VA. 20 divided 20 times VB is plus VB. 20 divided by 10 multiplied by VB is plus 2 VB. Those equations are almost equal and opposite there, but the fact that the current source on this side is 4 amps is going to mean that the voltage at B is different from the voltage at A, of course. Okay, so now we have here negative 2 VA plus 5 VB is equal to 4, and that is equation 2. And so now, you know, a substitution example here, because there's only 2 equations and 2 unknowns, relatively easy. And so you notice that mesh analysis up there, you know, you would have had 5 mesh equations. The voltage drops across the the current sources would have had to been and an extra copper, simplify the circuit before you start it would have been necessary because too many equations, right? And so here again, because there's only two equations, your substitution solution is a lot easier, of course. So that's one of the benefits sometimes of nodal analysis, of course. And so then our matrix solution would be equation 1 has a 5 and a -2 for coefficients, and a -2 and a 5 for equation 2. The inverse of that matrix multiplied by the matrix constants, which is 200, and I'm noticing that I got a mistake down here. Nobody pointed that one out. 20 times 4 is 80, and so this is equal to 80 down here. And if we don't get it correct, obviously, our solution is going to have an answer. But 20 times 4 means the constant down there is 80. Okay, good that we caught that. We put our 80 here. And we put that in the calculator now, and the answer comes out, and it is 55.2 and 38.1, and of course that is VA and VB. Oh, that's supposed to be B there. And so the answer to our original question is the voltage drop across the 4 amp source is VB equals 38.1 volts.